Okay, this video is to go over the last lesson in Unit 5, which is actually Section 7.1 in the textbook. Normally we do all of Chapter 7 in Calculus 12, but this year we're just going to do this one section, so I've put it in with Unit 5. Okay, so this is the last integration strategy we're going to be learning this year. So this is integration by parts. We're going to start with a proof of it, and then we're going to go into some examples. You don't need to know the proof, but we haven't done that many proofs this year, so I just wanted to give you some exposure. Okay, so we're going to start off with a product of two functions for our proof, f of x times g of x. And let's take the derivative of that. So the derivative of f of x times g of x would be f prime x times g of x, right? Using the product rule, plus f of x times g prime of x. So that's just the product rule. And then now let's take the integral of both sides of this. I'll write dx here, dx. Okay, so remember integrals and derivatives are opposites, so they kind of cancel out on the left side. So we just have f of x times g of x. And on the right-hand side, you can separate those two terms. So I'd have f prime x times g of x dx plus the integral of f of x g prime of x dx. And if we rearrange this, I'm going to move this term. Hold on, I'm just going to move this term I'm highlighting in yellow to the other side of the equation and move this term to the other side. So I'm going to flip those two terms. So I'm just going to rearrange the equation here. So it'll be f of x g prime of x. The integral of that is f of x g of x minus integral of f prime of x g of x dx. Actually, sorry, I misspoke. So I kept the yellow terms where they were and just moved the term I did not highlight to the left-hand side. That's what I did. So that is the integration by parts formula in the last step there. So I'm just going to highlight that. This is integration by parts. It looks messy right now, but it actually helps you solve integrals where you have a product of two terms. So we'll see in the examples. But that's how you get the formula. It comes from the product rule. And it's useful when you have a product of two terms that you're trying to find the integral of. Okay. Often it's written in this condensed format so that it's easy to remember. It's stuck in my brain now after teaching calculus so often. So integral of u dv equals uv minus integral of v du. It's like in my brain like the quadratic equation. You'll have a notes page on your test so you can write this formula down if you're having trouble memorizing it. So what you do basically is if you have an integral of a product of two terms, for example, u and dv, then you can rewrite the integral, or you can solve it, and it's equal to u times v minus integral of v times du. I'll show you what I mean by that in the example. Okay, so let's look at example 1. We have a product of two terms, x multiplied with sine x, and we want to take the integral of that. We would not want to use substitution here because it's not like one of those cases where we have a composition. It's more like a product. So you want to use integration by parts most often when you have a product. Okay, not a composed function. Okay, so we're going to have to pick here what our u is and what our dv is. So notice in the formula, we've got u in yellow and then dv in blue. So I'll just keep that so you can see it. So our u is going to be, you want to make the u something that gets simpler as you take its derivative. So if we make u equal to x, the derivative of that is 1. So that's a good thing. We want to make the u a term that gets simpler as we take its derivative. So we're going to make u equal to x. And then dv is going to be this part here. Sine x dx. Okay. If you rearrange that, that is, you can put the dx here. Oops, I wrote dx. You can divide both sides by dx. You'll have dv by dx equals sine x. So that's your blue part, and that's your yellow part. Okay, so we've split it into two parts. Now we're going to write the rest of the formula. The rest of the formula, as you can see, involves v, and it also involves du. So we need to write down what those are equal to. So if u is equal to x, then we find its derivative in order to find du. So du by dx would be 1. Just rearrange that equation. You get du equals to dx. So wherever there is, or 1 times dx, wherever there's a du in the formula, we're going to put dx. Okay, and then in order to find v, we need to find the antiderivative. So if the derivative of v with respect to x is sine x, v would be the antiderivative of that. So that would be negative cos x. Okay. So that's what I'm going to be replacing in this formula here. So I'm going to write the formula down. U dv equals uv minus integral of v du. Okay. So the integral of x sine x dx equals, so u is x, v is negative cos x, minus integral of v is negative cos x, and du is dx. Okay, so I got all of these terms from the yellows over here, and all of the v terms and dv terms from the blue over here. Okay, now let's see what we've got once we simplify this. So x times negative cos x is negative x cos x. I don't need to take the integral of that. That part is done. The two negative signs here can be multiplied together to make a positive. And look what's happened here to the integral. This integral I can solve. I do know the antiderivative of cos x, so I am going to solve that. So what integration by parts does is it breaks, sorry, the lights have turned off, there we go. It breaks it up into two parts, and usually if you choose your u and v correctly, it breaks it up into an integral that you can actually solve. So the solution would be negative x cos x plus, so the antiderivative of cos x is sine x, and then you need to add plus c onto the end because it's an indefinite integral. There we go. So the integral of x sine x dx is negative x cos x plus sine x plus c. Remember that you can always check your work. So if I take the derivative of my answer, I should get x sine x back. I'm just going to do this the one time, but remember you can check your work every single time you do an integral. So if I take the derivative of my answer, negative x cos x plus sine x plus c, I should get x sine x. And that's how I know I've done it correctly. Okay, the first part here requires chain rule. So I'll have negative 1 times cos, no, not chain rule, product rule. Negative 1 times cos x plus negative x, pen is acting up. There we go. Negative x times negative sine x. And the derivative of sine x is cos x. And the derivative of c is 0. Let's simplify. So I'll have negative cos x plus sine x. Oops. Plus x sine x. Plus cos x. And the cosx's cancel each other out, so we get x sine x, which is exactly what we started with. So we did do it correctly. So let's just overview what we did here. So we chose a u and a dv. The u should always, or should usually be something that's going to get simpler when you take its derivative. You don't want to make sine x equal to u because sine x does not become simpler when you take its derivative. Its derivative is cos x, which is kind of the same. You find du by taking the derivative. Now you choose dv to be the other part. So in our case, it was sine x dx. And then we do the antiderivative to find v. Then you write down the equation and replace all the parts and solve. Okay, so let's do another example. Ln x. This is a special example because there's just one term. It looks like it's not a product at all, but it is actually a product between 1 and ln x. So we are going to make ln x equal to u. You can't make ln x equal to dv because we don't know the antiderivative of ln x, so we have to make it u. So u is going to be our ln x, and dv is going to be 1 times dx. Okay. So the derivative of ln x, du by dx, would be 1 over x. So du equals dx. Rearrange it to solve for du, 1 over x dx. And we find the antiderivative to get v. So the antiderivative of 1 is just x. Okay, let me use my colors again to remind us. All right, so let's write down the formula. Integral of u dv equals uv minus integral of v du. So anywhere where there's a u, I'm going to replace my yellow terms. Anywhere where there's a v or dv, I'm going to replace with blue terms. Okay, so integral of ln x dx equals, so u is ln x times x minus integral of v, so x, and then du times 1 over x dx. Awesome. This actually worked out nicely because the x and 1 over x end up canceling out. So this is, and just conventionally, we tend to write x ln x instead of ln x times x. So I'll write it in that order, minus 1 times dx. Okay, and I know how to do the antiderivative of 1, so I will solve that. X ln x minus x plus c. We do need to be careful and write absolute values around the x here because you can't have a negative number in your ln argument. Okay, and that's it. That is the solution. So that is the antiderivative of ln x using the integration by parts method. Okay, let's do another example where we have to do a two-step integration by parts. Okay, and we're going to use the variable t instead of x, but it'll be the same thing. Okay, so here we have t squared times e to the power of t dt. So remember, you want to make your u something that's going to get simpler as you take the derivative. The derivative of e to the t does not get simpler when you take its derivative. It's just e to the t again. So you want to make the u t squared, since it's going to be 2t when you take its derivative, and then we're going to take the derivative again, you'll see, and it'll be 2. So you want to do the thing that's going to get simpler as you take its derivative. That should be your u. If you choose the wrong u, all you're going to do is end up getting an equation that's more complicated, and then you'll think to yourself, okay, well, I can't solve this, so I'll try the other way. So u is going to be t squared, and that means my du is going to be 2t dt. So once you get comfortable, you can already rewrite it write the derivative in the rearranged form. My dv is going to be e to the t dt. And that means the antiderivative will be e to the t. Okay, so let's write my little formula. So integral of u dv equals uv minus integral of v du. All the u terms, all the v terms. Okay, so integral of t squared e to the power of t is going to be t squared e to the t minus integral of 2t e to the power of t. I wrote the 2t in front, but just because conventionally that's what you do. Okay, so now I still cannot evaluate this integral because it's still a product of two functions, 2t and then e to the t. So I'm going to apply integration by parts one more time. So I'm going to choose a new u and a new dv and do this integral again. Okay, so this time my u is going to be the 2t. And du is going to be 2. And my dv will be e to the power of t. And my v will be e to the t. Okay, so at this point, I'm going to replace everything there. So I'm going to write the whole thing out, though. So my original integral equals t squared times e to the t minus, okay, so I need uv minus integral of v du. So uv is 2t e to the t. Sorry, my lights keep turning off. And my integral of v du is 2 e to the t dt. Okay, great. So I'll just write in red what this is. uv minus integral of v du. So that integral there, you had to use by parts again. Okay, so this is the case here. If you see a t squared, you're going to have to do integration by parts twice to solve it. If you see a t to the power of 3 or next to the power of 3, you're going to need to do it 3 times to solve it. Okay, so finally, I'll have t squared e to the t minus 2t e to the t. This negative sign and this negative sign cancel out, so I'll have plus. And the antiderivative of 2 e to the t, the 2 just comes out, and e to the t is just e to the t plus c. There we go. Okay, so let's just review what we did. So we had a product in our integral, so that's usually an indication you need integration by parts. We picked our u, we picked our dv, and we substituted it into the formula. And when we did that, we found that our integral still had a product of two terms. So for that new integral, we need to do another integration by parts. And when we did that, we found we could evaluate the final integral. So that's a two-step example. Okay, the last one is going to be a special case. Let's have a look. E to the x times sine x dx. I'm just going to write here special case. So it is a product of two terms, so good indication we need integration by parts. And if you recall before in the lesson, I said you want to choose the u to be something that's going to become simpler as you take its derivative. Let's talk about e to the x. If I make that the u, it's not going to become simpler as I take its derivative. It's just e to the x, e to the x, e to the x every time you take the derivative. But also sine x is not going to become simpler as you take its derivative either, because it just becomes cos x and then negative sine x and then cos x. So both of them don't really become simpler. However, we can use the fact that they're kind of cyclical in the derivatives to solve it. So I'll show you what I mean. I'm going to write the steps out I'm going to type the steps just just so that it's nice and clear. So step 1 is going to be choose u and dv. It actually doesn't matter which one you choose to be u and which one you choose to be v formula. So we'll just, since e to the x is written first, that'll be our u. So u is e to the x. So du would be e to the x dx. dv is going to be sine x dx. Antiderivative of sine x is negative cos x. Okay, so that's my dv, that's my v. Here's my u, here's my du. Okay, let's rewrite this formula. I'm going to write a little bit smaller because I need lots of space. E to the x sine x dx equals, so uv, so I'll have negative e to the x cos x minus integral of v du. So the two negative signs are going to cancel out because I've got a negative in my v term. V du, so I'll have cos dx cos x dx. Okay, and this is a plus sign because the negative in the v term canceled out with that. Okay, so that's step 1. Now, step 2 is choose a new u and dv, apply formula again. Okay, so in our new integral that we have here, we're going to choose a new u and a u dv. So I'm going to choose the u equals e to the x, and the dv is cos x dx. U equals e to the x. So it's going to look pretty similar. Du equals e to the x dx. And our dv is going to be cos x dx. So our antiderivative of cos x is sine x. Okay, great. So I'm going to rewrite the whole thing again. So we were trying to find e to the x sine x dx. And from the first step of integration by parts, we got this plus, and so now I'm going to have uv, so e to the x sine x, minus integral of v du. V du. So I'll have e to the x sine x dx. Okay. Last step. Notice I still have, I'm going to use green maybe to highlight, I still have an integral that I don't know how to solve at the end. However, look, we got back to, it is actually the identical integral from what we had at the beginning. That's weird. Okay, so it's kind of cyclical, like I mentioned before. So we're ending up with the same integral we already had at the beginning. I'm going to move this term to the left-hand side. So to both sides of the equation, I'm going to add e to the x, oops, my pen is just really acting up today, sine x dx plus integral e to the x sine x dx. So add the integral term to both sides. Okay, let's see what we've got. So now we have 2 of those on that side. 2 e to the x sine x dx equals negative e to the x cos x plus e to the x sine x. Okay, cool. So if I just divide by 2, I have my answer. Kind of weird. So we didn't. So the integral of e to the x sine x dx is just, I'll pull the, dividing by 2, I'll just pull it out as a half. Negative e to the x cos x plus e to the x sine x plus c. And that's it. So even though it feels like we didn't really integrate, we kind of did. So that's a very special case of the integration by parts formula. So it occurs when you have 2 sort of cyclical functions that keep giving you the same types of answers when you take their derivatives. So you do it twice. You'll end up with the same integral highlighted in green here. You add it to the other side, and then divide by 2, and you're good. Okay, I would recommend you do all of the assignment questions today, you're going to need a lot of practice with integration by parts to get it right. And it's also just a good practice in general of like all your integration techniques, because you'll need all of them to do these questions. And so it's a good little review of the unit as well. Okay, so I'm going to stop video.